Alrighty, hello and welcome to Tuesday evening's lecture. We're continuing here in chapter 9. We're going to be dipping into a discussion of how acid-base reactions are related to stoichiometry, which is going to be awesome. And we're going to begin that discussion with where we left off last Thursday, which was a question about this reaction. Okay, there we go. Which was, we had talked about how water can be an acid or a base, depending upon what it's reacting with. So we posed the question, what happens when liquid water is left alone with liquid water? What happens when it reacts? What are the two products of this reaction? Now, to determine the products of this reaction, we need to so this is an acid-base reaction. Water is going to be both the acid and the base in this reaction. Now, either water can be an acid, either water can be a base. So we're just going to artificially label them. I'm going to label this first water as the acid, and I am going to label the second water. I'm going to do a contrasting color. Let's go. Sorry, said I was going to contrast it. There we go. We're going to label this second water as the base. Now, let's start with this base, this water molecule, which is going to function as our base in this reaction. A base, you'll recall, is a proton acceptor, which means that it is going to accept H+. So H2O, after it accepts a proton, H+, is going to turn into H3O+. All right? And then looking now to our acid, the water molecule that reacts as an acid is a proton donor. It's going to lose a hydrogen and it's going to lose a plus charge. So it is going to become OH minus hydroxide. All right? So this reaction has a name. This is called the self-ionization of water. Water will react with itself to produce hydronium and hydroxide. Now, the hydronium ion, this H3O+, is the conjugate acid, and the hydroxide is the conjugate base. All right? Now, okay, so as you'll notice, this reaction is an equilibrium. Right, there is a forward reaction and a reverse reaction, and as we learned last lecture, for any equilibrium, you can write an equilibrium constant. This equilibrium constant gets a special label. This is called Kw, because it is the equilibrium constant for the ionization of water, so Kw. Um, as we know, right, and this is just a quick refresher, KEQ is equal to the concentration of products over the concentration of reactants, right? So you do your concentration of products over reactants. So our products are hydronium and hydroxide, but our reactants for this reaction, you'll notice, are both in the liquid phase. And we know that solids and liquids do not show up in an equilibrium constant because they have a constant concentration, right? They're pure substances. Their concentration doesn't change. And so we do not include solids or liquids, which means Kw doesn't have a denominator, all right? It's simply the acid ionization constant is equal to the concentration times the concentration of hydroxide. Oops. All right. Now, Kw has a value. All right. When you solve for it, we can determine it experimentally, and Kw is equal to 1.00 times 10 to the negative 14. That is the value of this equilibrium constant. Now, think about this. This equation has some very interesting implications for acid-base chemistry. We know from, and a quick reminder, from the Arrhenius definition. I'm misspelling his name. I think there's a second R in here. Let me double check. Oh, there's a double R, and I messed up my H placement. Forgive me, font. It's font Arrhenius. You'll recall that the Arrhenius definition of an acid and a base says that an acid produces H3O plus, and a base produces hydroxide, right, according to the Arrhenius definition of acids and bases. Now I want you to think for a minute about what happens if the concentration of hydronium increases. If you increase the concentration of hydronium, hydroxide, hang on, I'm not just going to say this to you. I'm going to prove it to you mathematically. We can do a little bit of algebra here. And let's use this equation to solve for the concentration of hydroxide, for example. So if we divide both sides of this equation by the concentration of hydronium, this is the equation we end up with. The concentration of hydroxide is equal to 1.00 times 10 to the negative 14th over the concentration of hydronium. And you can see that hydroxide is in the numerator, hydronium is in the denominator, so these two are inversely proportional. That means if the concentration of hydronium increases, because it's the denominator of the expression for the concentration of hydroxide, you got a denominator getting bigger, that means the concentration of hydroxide is going to drop. Conversely, if your denominator gets smaller, if the concentration of hydronium decreases, then the concentration of hydroxide is going to increase. So these two concentrations mathematically are inversely proportional. When one gets bigger, the other gets smaller. Now I want you to think of this principle in terms of Svante Arrhenius' definition. Don't think of this as the concentration of hydroxide. Think of this as the concentration of base. Don't think of this as the concentration of hydronium. Think of this as the concentration of acid, because this is true of every solution. When the concentration of acid in your solution increases, the concentration of base drops. When the concentration of base increases, the concentration of acid drops. The two are inversely proportional. So when a solution gets more acidic, it is at the same time getting less basic. When a solution gets less basic, it is simultaneously getting more acidic. All right? Now, all right, let me see where. Okay, so this principle allows us to solve problems like the following. Oops. There we go. All right, we can solve problems like the following. What is the molarity of hydronium in a solution of in a solution of 0.100 molar NaOH. All right. So first, we want to identify what we're trying to find. And we're trying to find the concentration of hydronium. All right? Now let's look at what we're given. We're given that we have a 0.100 molar solution of sodium hydroxide. Now, if you're thinking, oh, it feels... Wait, hang on one second. I forgot to put this in a new layer. There we go. All right. If you're thinking, oh, it feels a little fishy that we're being asked about acid and we're given a thing with sodium hydroxide, that's good. Because another equation that you should totally have on your equation sheet is Kw is equal to the concentration of hydroxide or hydronium times the concentration of hydroxide. Write that sucker down on your equation sheet. Not for the exam that went live today, but for the final. And also, you should just have this value of Kw written down as well, 1.00. times 10 to the negative 14th. And some of you may have astutely noticed, you're like, Josh, this is the concentration of hydroxide, but we were given the molarity of sodium hydroxide. Those are two different things, and you're correct. We need to determine what the molarity of hydroxide is. We can't necessarily use the concentration of sodium hydroxide. How do we do that? Remember, this is where solubility rules come into play. Anything that's paired with sodium is aqueous. And we know that aqueous ionic compounds split up into their constituent cation and anion pairs. All right? And from this, we see that there's a 1-to-1 mole ratio between sodium hydroxide and hydroxide. How does that help us? I'm so glad you asked. If you split up molarity into its numerator and denominator, it's moles of sodium hydroxide in the numerator over liters. This balanced chemical equation gives us the conversion between moles of sodium hydroxide and moles of hydroxide. Because it's a 1-to-1 ratio in the balanced chemical equation, we can cancel moles of sodium hydroxide, which leaves us with 0.100 molar hydroxide. So at this moment in time, we just found our molarity of hydroxide. We know Kw. We can solve for our concentration of hydronium. Oops. We just have to do a little bit of algebra first. So we have Kw is equal to the molarity of hydronium times the molarity of hydroxide. First step, we're going to divide both sides by the molarity of hydronium. So cancel, and we're left with the expression, the molarity of hydroxide is equal to Kw over the molarity of hydronium. Oh wait, I'm so sorry. We need to solve for hydronium, not hydroxide. That is my bad. The algebra is going to look very similar, but I think it's just faster rewriting it than trying to control Z my way to the end. Let's divide both sides by the molarity of hydroxide, maybe. And then we'll know the molarity of hydronium. There we go. And now we can plug in our values. So molarity of water, or the acid ionization constant of water, 1.00 times 10 to the negative 14th over 0.100 this gives us a molarity of hydronium of 1.00 times 10 to the negative 13th molar. And that is the molarity. All right. Let's do another example. All right. What is the molarity of hydroxide in a solution of 3.00 molar of hydrofluoric acid? That's not a period, that's a question mark. HF has a percent ionization HF is a percent ionization of 2.6%. All right. So, first, we have to remember what to do with our percent ionization. Well, actually, first, what do we want to find? We want to find the concentration of hydroxide. And you'll notice that we're given, so hydroxide's a base, and we're given information about an acid. When you're asked about a base, but you're given an acid, I guarantee you, you're going to need the self-ionization of water. All right? Because this is the thing that connects the two of them together. The equation for the self-ionization of water Kw is the concentration of hydronium times the molarity of hydroxide. And you'll notice, we're being asked for this. You always know Kw because it's written on your equation sheet. That means solving this problem hinges on our ability to find the molarity of hydronium. Now, the only other pieces of information we're given is the molarity of HF and its percent ionization. So how do these connect? Remember, so actually, give me 1 second here. Yeah, we covered percent ionization last time. Did we? Hang on, I'm sorry. I feel like we did, but I just want to double check. Whoa. Maybe we did. I'm so sorry. Oh wait, no. Here we go. Yes. Okay. 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 Yes. Okay. Good. 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 We talked about Kas. We talked about percent ionization. Okay. Sorry. I was looking at my notes and chronologically, we had, but then I started doubting myself, wondering if we had gone out of order. So we've talked about how to handle percent ionization. So remember, the acid ionization between HF and H2O. Water's going to react like a base here. It's going to accept a proton, becoming H3O plus, and HF is going to become F minus. And this ionization constant means that 97.4, I think. Let's look at the math. 100 minus 2.6%, yeah, means that 97% of our HF is going to remain. It's not going to react. But, oh, sorry, not 97, 97.4 is going to remain associated. But 2.6 of it will form hydronium and fluoride. That means that the concentration of hydronium, the molarity of hydronium, is equal to the molarity, that initial molarity of HF, times 2.6%, or 2.6 over 100. All right? Because that's the amount of HF that generates hydronium in this problem. So 3 times 2.6 divided by 100. Gives us a concentration of hydronium equal to 0.078. That's what my calculator tells me. I know, however, that I need to have, well, let's see, actually. This is 3 sig figs. This only has 2, so I actually have to stop at 2 sig figs, so that's where I stop. This is my concentration of hydronium. Now that we know concentration of hydronium, we can use the equation for the acid ionization constant of water to find our concentration of hydroxide. Oops. There. So Kw is equal to the molarity of hydronium times the molarity of hydroxide. If I divide both sides by the molarity of hydronium, I can solve for the molarity of hydroxide. So I have Kw over hydronium. It's my new expression. So Kw is 1.00 times 10 to the negative 14. My molarity of hydronium is 0.078. So my molarity of hydroxide rounded to 2 sig figs will be 1.3 times 10 to the negative 13. Let me just double check that. Yeah. Molar. That is the molarity of hydroxide in this solution. So that's how you handle a problem where they throw out percent ionization. Let's do another example. Determine the concentration of hydroxide and the concentration of hydronium in a solution where there are equal amounts of both. All right. How do we solve this? What we want to find is the molarity of hydroxide and the molarity of hydronium. And the key to solving this is this: equal amounts of both. That means if there's equal amounts of both, that means the concentration of hydroxide is equal to the concentration of hydronium. And so we can make a substitution into the equation for the self-ionization of water. Because if these two are equal, then we can substitute in the concentration of hydronium for the concentration of hydroxide. They're the same quantity. So you do a substitution. This means that Kw in this case would be equal to the concentration of hydronium squared. And we can solve for the concentration of hydronium if we take the square root of both sides. So the concentration of hydronium would be equal to the square root of Kw, which turns out is 1.00 times 10 to the negative 7 molar. And if you're wondering, your concentration of hydroxide is going to be the same thing. All right? Because, as we said at the beginning of this problem, the two are equal. The two are equal. Now, this solution has a special designation. This is known as a neutral solution. A solution is neutral when it does not favor acid or base, that acids and bases are present in the same amount. That's what it means to be neutral. So notice, it doesn't mean that there are no acids and there's no bases. It just means they're both present in the same quantity. All right? That is what it means to be neutral. Now, we've been using a lot of scientific notation recently. A lot of scientific notation. And it gets cumbersome to write, times 10 to the power of whatever, right? It's a little much. And so chemists have just not discovered, I shouldn't say that. This is not something we found in nature, this is something we made. We developed a system, a scale, to make the numbers easier to communicate as far as concentration of hydronium and hydroxide go. And that scale, is called the pH scale. The pH scale is a way of rating how acidic a solution is. And the equation for it is as follows. pH is equal to -1 times the logarithm of the concentration of hydronium. Now, something that I want to tell you right out of the gate, you know that this is a very sig fig heavy class. I'm a very sig figs forward instructor. I emphasize it heavily. And I'm here to tell you that you don't need to worry about sig figs and pH. There is a different set of rules for handling significant digits and a logarithmic scale, which is what pH is. And I just don't want you to worry about it. So this is the one time in the class where I'll say, don't worry about it. You don't have to worry about sig figs when it comes to pH. Now, let's, you will have to calculate them. You will have to use this equation. But you won't have to apply the rules for sig figs. All right. Let's apply. Sorry, this equation. I messed up. All right. pH scale. Calculate the pH for the following solutions. All right. Solution 1 has a concentration of 1.00 times 10 to the negative 12. Solution 2 has a concentration of hydronium of 1.00 times 10 to the negative third. All right, now, before we calculate our pHs, first I want to ask you something. Which solution has more acid? To do that, you compare the exponents of 10. This is a negative 3. This is a negative 12, so that's much less, right? Because it's a negative exponent. So solution 2, I hope you'll agree, is more acid than solution 1. All right, now let's calculate our pHs. So 1 times 10 to the negative 12 gives us a pH of 12, and 1 times 10 to the negative third, take the logarithm of that. This has a pH of 3. Notice the solution with more acid has a smaller pH. The solution with less acid has a larger pH. So the pH scale, on the pH scale, the smaller you are, the more acidic you are. The larger you are, the less acidic you are. Or, we could say conversely, the more basic you are. All right, so it's reverse, it's inverse. The smaller you get, the more acidic you are. The larger you get, the less acidic you are. All right. The second thing that I want to point out is that the pH scale is a logarithmic scale. What does that mean? That means, for example, let's say you had a solution that had a pH of 4. Versus a solution with a pH of 3. Even though the difference here is only 1 unit, right? It's only 1 lower. Because it's logarithmic, that means that this is 10 times more acidic. It's a power of 10. If you compare pH 4 versus pH 1, that's a difference of 3, right? This is 10 to the third times more acidic, or 1,000 times more acidic. All right, so every unit of 1 on the pH scale is an exponent of 10 in the magnitude of the difference in the amount of acid. All right, so it's huge. 2 units is 100 times. 3 is 1,000, etc. So that's one thing that you need to keep in mind of the logarithmic scale. All right. Um, there's an important number on the pH scale, and it comes from our understanding of a neutral solution. We already did a problem a few minutes ago where we found the concentration of hydronium and hydroxide in a neutral solution, right? And a neutral solution is defined as a solution where the amount of hydronium is in solution is equal to the amount of hydroxide. All right. So we calculated that concentration. It's 10. It's 1 times 10 to the negative 7th molar. All right. If you find the pH of a neutral solution, therefore, the pH of a neutral solution is 7. At pH 7, that's called a neutral pH because there is a balance, a perfect balance of acid and base in solution together at the same time. There's the same amount of acid, same amount of base. So this is the middle of the pH scale. When you have pH 7, this is neutral, which means the amount of acid in solution is equal to the amount of base. If you have a pH that is less than 7, pH less than 7 means that your solution is acidic because there is more acid present in solution than there is base. And finally, if you have a pH that is greater than 7, this would tell you that your solution is overall basic because the concentration of acid in solution is less than the concentration of base. So this is the three classifications of solution. Either you're neutral at pH 7, you're acidic at a pH that is lower than 7, or you are basic at a pH that is higher than 7. All right. Okay. I'm going to go a little bit out of order here. I'm going to go a little bit out of order, mostly because I want to touch on the topic of titrations, which I've had some really good conversations in lab about titrations. The last hurrah for the E-Lab situation all have to do with titration experiments. It's a type of experiment. It's very important, very prominent. And I haven't covered it in lecture. We've talked a little bit in lab. Those of you know who you are, who've showed up and asked me, we've walked through some stuff. So for you, it'll be a little bit of review. But we're going to cover the topic thoroughly because this is what the end of our lab is based on. So let's talk about titrations. All right. Now, um, often I'll hear students talk about titration reactions, but that's technically incorrect. A titration is not a type of reaction. A titration is a type of experiment. Oops. Oh, cool. Okay. It's an experiment, very vaguely, it's an experiment in which a known quantity is used to determine an amount of unknown. All right. Um, Often, but it's not exclusive. Um, the amount it could be a concentration. So to determine the concentration of an unknown solution, very common practice in a titration. Your known has a name. Oops. Your known is referred to as the titrant. Likewise, your unknown has a name. Oh, just realized I wrote unknown. Your unknown has a name. Your unknown is called the analyte. All right? Okay. So that's very vague. Let's get into the nitty gritty. So, the most common piece of glassware used in a titration is called a burette, and it's kind of like a long graduated cylinder. Um, that drains from the bottom. So there's a kind of a valve. This is called a stopcock, which you can open or close to let the solution to drain the solution from the bottom. And it's drained into typically an Erlenmeyer flask. Now this isn't absolutely the way it has to be, but this is often the setup for normal titration. You will have your analyte. Yeah, so your analyte, sorry, in the Erlenmeyer flask. So you'll have your analyte down here, your titrant up in here. You mark the volume where you start. This is the titrant. And this is the analyte. And what you do, so the titrant and analyte react together. And what you do is you drain your titrant. You open the stopcock, and add it to the analyte until the two are done reacting. Oops. Once they finish reacting, you close the stopcock. Usually the end of the reaction will be accompanied by a color change. You record your second volume. And remember, your titrant is the known quantity, which means under most normal experiments, we know the molarity, and we can find the volume used for the reaction, right? Because this is final minus initial. Multiplying these together will give us our moles of titrant. And then we can use a balanced chemical equation to go from moles of titrant to moles of analyte. All right, and that's how you use something with a known concentration to determine the amount of moles of analyte present in a sample. All right, so that's kind of the conceptual background. Let's actually do a titration problem. All right, so so consider the following example. H2SO4 or I should say, excuse me, sorry. (10.00 milliliters) of sulfuric acid are titrated with 2.50 molar sodium hydroxide. The initial volume of sodium hydroxide was 0.05 milliliters, and the final volume of sodium hydroxide is 12.48 milliliters. What is the molarity of sulfuric acid? All right. First thing you want to do, identify what you are trying to find. We want to know the molarity of sulfuric acid Molarity has an equation. It's going to be worth your time to write it down. The equation for molarity of sulfuric acid is moles of H2SO4 over liters. So we need two things. We need the volume of H2SO4 and we need the moles of H2SO4. One of the things that you'll notice is we're given the volume right here. It's 10 milliliters. Granted, we got to convert that to liters, right? But once you do, you're home free. We got our denominator. The only real question is how do we get at that numerator? Actually, I'm going to change colors. Well, the only other information given is all info about sodium hydroxide. You can see that. Initial and final volume of sodium hydroxide, moles of sodium, or molarity of sodium hydroxide. So we are going to need to somehow use molarity and volume of sodium hydroxide to find moles of sulfuric acid, right? Because we have the molarity and the volume. Well, molarity is equal to moles over liters. We know molarity, we know volume, so we can find moles of sodium hydroxide. That isn't going to do us any good without a balanced chemical equation. So the number one piece of advice I can give you anytime you're doing a titration, get yourself the balanced chemical equation, because you're not going to be able to solve the situation without it. So the balanced chemical equation between, just going to clear a little room here, sulfuric acid and sodium hydroxide. You might be going, Josh, I can't write a balanced chemical equation. I don't know what the products are. To which I'll say, you got to figure it out. Literally, this is a neutralization reaction, which is one of those reactions where I don't need to tell you what the products are, because the products are always two things: salt and water. Water is easy enough. H2SO4, nope, it's sulfuric acid. H2O is water. The salt, however, takes a little bit of digging. The salt is made up of the metal from the metal hydroxide, so that's sodium, and the leftover piece, the conjugate base of the acid, right? So this is sulfate, which means our salt is going to be Na2SO4, and it's aqueous because anything paired with sodium is soluble. Oh, I did not mean to do that all in the same layer. All right. Oh, so now we know what the salt is. It's not just a word. We actually have a chemical formula. Now we can balance. We have hydrogen, sulfur, oxygen, and sodium on both sides of the chemical equation. We have 2 hydrogen from sulfuric acid, 1 from sodium hydroxide, 1 sulfur, 4 oxygen from sulfuric acid, 1 from sodium hydroxide, and 1 sodium ion. We have 2 hydrogen 1 sulfur, 1 oxygen from water, plus 4 from sulfate. Then we have 2. All right. Let's balance this thing. Always go for the easy stuff first. And the easiest thing that pops out to me is sodium. We got 2 on our product side, only 1 on our reactant side, so we need to multiply sodium hydroxide by 2. This is going to change. We don't just have 1 oxygen now, we have 2, same with hydrogen. 2 plus 2. 4 plus 2. All right. Sodium's balanced. Now we got to figure out hydrogen and oxygen. Hydrogen seems simpler to me. So we're going to multiply water by 2. This changes my hydrogen count and my oxygen count. But it just so happens it balances both of them out simultaneously. So this is my balanced chemical equation. And with this, I can find my moles of sulfuric acid. First, I need to know my volume of sodium hydroxide. It's going to be final minus initial. So final volume 12.48 milliliters minus 0.05 mils. 12.48 minus 0.05 gives us a volume of 12.43 milliliters. My sig figs are spot on because my last sig fig in both of these numbers is in the second decimal place. My answer has its last sig fig in the second decimal place, so nothing needs to change. Next, I need to convert this to liters. So we put milliliters in the denominator, liters in the numerator. So my volume of sodium hydroxide is 0.01243 liters. All right, now I can use that in conjunction with my molarity of sodium hydroxide. Just moles of NaOH. Moles per liter. Times my volume in liters of sodium hydroxide. Now liters cancel. And now I can convert moles of sodium hydroxide to moles of sulfuric acid. And we can see from the balanced chemical equation that it is a 1 to 2 molar ratio. So I cancel those. Now I crunch my numbers. All right. So we had 0.0155 moles of H2SO4. Now, at this moment in time, it might be super tempting to just box it and just say, that's our answer. But that's not what we were asked to find. Unfortunately, we were asked to find the molarity. So, we're not quite there yet. We're almost there, but not quite. All right? So first, we need to take our volume of sulfuric acid and convert it to liters. So we have 10.00 milliliters of sulfuric acid. There's 1,000 milliliters in a liter. Milliliters cancel. So our volume of sulfuric acid is 0.01000 liters. Got to remember, start with 4 sig figs. We end with 4 sig figs because this unit conversion is within the metric system, so it is exact. We are finally poised and ready to calculate the molarity of sulfuric acid. Is moles of sulfuric acid, 0.0155 moles over liters. So this comes out to be 1.55 molar H2SO4. And this is our actual final answer. All right, this is the solution to our problem. This is not the end of titrations. We're going to talk more about them next week, but I want to end with just a warning. Students are often tempted to use this equation for titration problems. The dilution equation, M1V1 equals M2V2. Now, this is for dilutions, not titrations. And the thing is, it only works sometimes, which is what I'm here to warn you about. And I'll tell you when it works, and I'll tell you won't. So you can use it intelligently. But just be careful. The dilution equation only works for titrations if, all right, and this is what it all hinges on, if there is a 1-to-1 mole ratio between titrant and analyte. All right. If you have a 1-to-1 ratio between titrant and analyte, this equation will work. If you don't, it will give you the wrong answer. And I want you to notice something. The example we just did. Is there a 1-to-1 ratio between titrant and analyte? There's not. So if you try to use the dilution equation on the example we just did, you'll get the answer wrong. And I'm going to make you a promise. I'm going to make you a promise. The problems on the exam will largely, if not exclusively, be titrant and analyte problems that are not 1-to-1 ratios. So I caution my students to stay away from using this in the exam context and out of it. But if you choose to use it out of the exam context, you have to make sure there's a 1-to-1 ratio between titrant and analyte in the balanced chemical equation before employing the dilution equation in the context of titrations. All right. I'm going to leave off with an example today. We're not going to start it. We'll start it on Thursday as we wrap up chapter 9. Poised to wrap up chapter 9 on Thursday. I'm going to leave you with this. Give it a try. We'll open lecture by starting this. KHP is an acid that reacts with sodium hydroxide in a 1-to-1 ratio. The initial volume of the sodium hydroxide solution was 1.03 milliliters. The final volume of the sodium hydroxide solution was 14.96 milliliters. This volume of sodium hydroxide was added to 25.0 grams of KHP dissolved in 20 milliliters of DI water. Determine the molarity of the sodium hydroxide solution. All right, so we're not going to start this today. We'll crack into this on Thursday. I'm going to pause, but I'll be back in about 15 minutes to start open office hours for lab. Later, dudes.